Good morning friends, and welcome to this presentation on Introduction to Design Verification. Myself Tilak Meka. I am a senior manager at Synopsys India. In this presentation I am going to talk about RTL design for ASIC flow. ASIC stands for Application Specific Integrated Circuits, or shortly called as integrated circuits as well, or simply as IC also. While IC design and verification is a complex flow, the primary idea of this webinar is to make you understand the various verification strategies and also help you with various verticals in the verification so that you can choose a career in the verification path. So, as you have seen, the RTL design complexity or the IC design complexity has been increasing over the past few years or past few decades in fact. While IC design complexity has been increasing, so is the verification complexity, and we need this complex verification system so as to enable quality products are available for the end users in a shortest time period. So, in this presentation we are going to look at the various verification techniques, and we can take the questions also during this course. So, this will be the agenda for today's session. So, first we will look at RTL verification. What is meant by RTL verification? RTL stands for register transfer level. It is a representation of your design in one of the HDLs. HDL is hardware descriptive language. So, it could be Verilog, VHDL, SystemVerilog, or any other HDL as well. So, we will look at what is meant by RTL verification, and then we will follow on with various verification techniques which involve simulation for this RTL. So, which includes dynamic simulation for RTL, which also includes the gate level simulations for netlist designs. And then we will look at what is meant by formal verification and static verification. And when we come to a complete system level verification, slightly we have to go for higher level objectives as well, which is for a system level design, which is also called as SoC, system on chip. So, we look at what is the system on chip design and verification flow. So, the objectives of this webinar, like once this webinar is done, you should be able to describe what is RTL verification. You should be able to use a SystemVerilog based language based test bench for dynamic simulation. Typically, we are all aware of like some of the HDLs like Verilog, VHDL. Here in this session, I am going to introduce you to SystemVerilog language, a high level constructs, and I also show what kind of test bench architecture looks for this SystemVerilog based test bench. And then we look at formal and static verification, and you should be able to explain what is an SoC, the system on chip, and the corresponding design and verification flow. So, why RTL verification? RTL verification is a mechanism in which we ensure the design is following its specifications. See, whenever we are trying to design a specific requirement, we look at the design from various requirements. Like let us say if you are having a full adder circuit, you want to design a full adder, you will be having input specifications, how many inputs are there, what should be the operation of the design, and what should be the output of the design, which will be sum and carry and so on. So, RTL verification is to ensure my design is conforming it to its specifications or the requirements. Now, the question will be why RTL verification? Why can't we design and take it to the next steps? So, let us take in history, right? Let us take one of the examples from the history. So, probably around in 1990s, one of a leading processor company, they introduced a new generation processor. Now, when this processor was introduced and it went into the PCs or personal computers, it was found that there was a floating point division issue. Now, what happened was the processor company had to recall all those processors back, and there was a huge expenditure, maybe in the tunes of $480 million, which in today's world it would be more than $1 billion. And then all the processors had to be fixed or had to be revamped for the new for the fix as well. So, and this processor was built on top of the previous processor, and the functionality was exactly same, but still it missed, and there was an issue with because of that missing check in the final product. So, RTL verification is very essential because it can lead into issues with the final product as well. And if you look at the RTL designs, like previously we used to have ICs with few tens of transistors, but now in today's ICs we see billions of transistors. So how do we do a smart way and ensure the product is still good and available to the users in the shortest format? That is what RTL verification constitutes for. So before we get into the RTL verification, let's take a step back and understand what was the entire ASIC design flow. And the following flow chart may be a little bit complex, but let's understand what are the various verticals available as an opportunity to an aspiring verification engineer or a design engineer. So this is the complete ASIC design flow. The design flow starts from the specification. This is the stage where we are capturing the requirements of your design. Once the design is specced or requirements are captured, we go to the phase where we do the RTL designing by using one of the HTLs. When we are using HTLs and we do RTL design, when the RTL design is complete, we move to the stage of RTL verification. This is the one which we are going to target in this session. Once it is a clean RTL, like the tests have been run and we ensure that RTL is good, we go to the next phase, which is the synthesis stage. Synthesis is the stage where we convert the high level language into a netlist format. So once the synthesis is done, we are going to the place and route, which is also called PNR, and this will create the schematic diagram of your design, and this schematic diagram is finally used for fabrication. So this is the flow: specification followed by RTL design, followed by synthesis, PNR, and finally the fabrication. Now if I have to kind of like create the verticals in the industry, I can say there is this design and implementation field where the designers will be doing the RTL designing or the gate level netlist, and also they will be developing the IPs. IP represents an intellectual property. It's a kind of like a small block of the design which can be reused across multiple designs. So you can create a career in the design or the implementation side, or you can also look at the verification aspect. Verification is the one where you will be ensuring the verification that the design is proper in terms of it's fully verified, fully validated, all the test cases are run, and it happens at multiple places. So you can create your career in the verification. And the other career is the backend career where you are going to do the PNR. So you can take your career either in the implementation side or the logical designing side, IP developer side, or on the verification side, or in the backend side. This is the complete ASIC design flow and the various careers which are available here. Now let's look at what are the various IC design verification technologies. Like I said, IC represents integrated circuits. Now depending upon the design requirements, you may choose either one of these verification technologies or a multi of these verification technologies. Typically in the industry, we use many of these verification techniques to ensure our verification is complete. So first one is a simulation. Let's take an example, the same example we have been talking about, adder. So we have a 2 input adder, each input is a 1 bit, and we are performing some addition with respect to this adder. Now how can I confirm that this adder is working correctly? One way is to apply the various inputs and then look at the output of the adder. So if I apply 0 0 0 1 1 0 and I monitor the output, that is the simulation. You create the test vectors and you apply these test vectors to the design and finally look at the outputs. Next is a formal verification. Like we have seen previously, when we are trying to when we are going through the ASIC design flow, initially we were looking at RTL design, then we moved to synthesis. Now how can we confirm the output of the synthesis is functionally equivalent to the RTL design? That can be achieved by formal verification. Formal verification helps you to do the equivalence checking between the RTL design and the netlist. Formal verification also helps you to with various applications like property verification and data path validations and so on. Next is a static verification. So, typically different designers and different engineers may use their own way of coding the design. Now, that may lead into some unknown issues or unsynthesizable constructs in the later cycles. So, in order to identify such kind of constructs right up front, we have static verification as well. Now, while these simulation, formal verification, static verification can be done at a block level to system, maybe a sub block level to a smaller system levels, but if you want to do a complete system on chip level validations or verifications, you take what is called as a emulation step. In case of emulation, you are going to use the entire SoC or system on chip, put it on an emulator along with the software as well. See, previously, if you are trying to achieve the same functionality in simulation, it's going to be very difficult because it is limited. Simulation is limited by the machine capacity. So, if your machine is smaller, like 32 GB, 64 GB, 128 GB of machine where you are trying to simulate is fine, but if you are going beyond that, you will be having very expensive simulations and very slow running simulations as well. So, in order to overcome such kind of challenges in the industry, we have an emulation step. Now, we can take the same example as an adder, right. So, we had initial an adder. Let us say this adder goes into an ALU block, which is an arithmetic and logic unit. Now, this ALU block goes into your processor, and maybe this processor block creates a complete system on chip, which is a mobile platform, for example. Now, if I want to do a camera testing along with the mobile SoC, I can maybe be able to do one single video frame, but I may not be able to do the complete mobile testing at a hardware level along with the software with a running video. So, if you have to do that, I go for the stage what is called as prototyping. So, in case of a prototyping, you will implement the hardware and then apply this hardware onto your integrated circuit design onto the special system, and then you can validate that kind of designs as well. So, that is the prototyping. Okay, so now we looked at RTL verification. RTL verification is a register transfer level verification where we verify the design across the various through various techniques, verification techniques, and now we are going to do a little bit deep dive into each of those. So, do understand that this is this may be a bit involved, but the idea again here is to make you comfortable with the verification flow and the aspects of the verification flow. Now, again if I come back to let us say a simplified ASIC design flow, this is a simplified ASIC design flow where let us say I start with the specification first and then I go with the RTL design. Once my RTL design is ready, I am going to do the logic simulation. So, for logic simulation you need to have your design ready. So, during the logic simulation I am going to apply various inputs, test inputs to that RTL design and monitor the outputs. That is the simulation aspect of this. So, I mentioned some tools here. This is basically from Synopsys, but there are equivalent tools available in the market which perform the same things. So, see all these things you do not have to do manually. You have to write a test bench, which is a manual effort, but then once the test bench is ready, you have simulators available which can simulate your design with the corresponding RTL test bench. Now, what is simulation? So, like we discussed, so simulation is to dynamically send some inputs to the design and then monitor the circuit responses. So, that is a simulation. And so, let us say our design is like this. This is netlist kind of design. Let us say I am having some inputs, set of inputs. I will be applying those inputs to your design and monitoring the output. So, that is a simulation. So, simulation means the RTL design is applied with some set of test vectors as inputs and the output is monitored. So, if I have to explain a dynamic simulation can be applied to the RTL design, which is a high level language where we use the RTL design, as well as it can be applied to the post synthesis output design, which is the netlist design or the gate level design. So, you can apply this simulation techniques to both RTL as well as the gate level simulation. Now, whenever we are talking about certain gates, there is a certain propagation delay associated or the gate delay associated, and why is that? because when we are looking at a VLSI integrated circuit at a maybe at a micro level, right. So, there are the resistances and capacitances introduced by the wires and the gates do cause certain delays for the inputs to be propagated to the output, right. So, because of those delays your input and output may not be happening at the same time. So, there is a certain delay, and if you are to simulate with those delays, so we can still be able to make use of simulation with a delay format known as SDF or standard delay format, which will provide you a timing model of your design, and you can simulate your actual design along with the delays associated with that design, and then look at the proper responses at the output. Now, what are we trying to confirm here? We are looking at functional correctness of your design, right. So, is the circuit doing what it is intended for? If the circuit is for adder, is it properly adding it? Is it able to take care of the carry and propagate the inputs to the outputs within some specified time limits or not? So, all those checks can be done with the simulation. Now, if I have to apply, so let us take the same example as an adder, right. So, if I have to say that okay, my adder is working correctly with all kinds of inputs. So, I have to apply each kind of inputs to ensure my adder is fully working, right. So, I have to ensure the scenario of 1 1 is also captured, because when I am adding 1 and 1 it will result as sum as 0 and carry as 1. So, is it all the scenarios of your design are correctly verified or not? So, you have to simulate with lots of input stimuli. Now, whenever we are talking about simulation, one of the most important items in the simulation is it's a most easiest mechanism to simulate your input design, but then the simulations are slow when it comes to maybe at a system on chip level or a subsystem level with very larger designs, like I mean maybe at a complete mobile SoC, if I say that, which has processors, memory and all the different components, camera unit, everything. If I have to simulate with that design, it will be going to be very slow. So, I have to ensure my simulations are fast enough. I am not wasting any specific elements in your design which are doing the time time consuming. So, I ensure my circuit is running fast enough. And in simulation, typically if you are using let us say Verilog, there is a scope for race. A race is a where the outputs are ambiguous. Let us say I have two assignments for values, one is a is equal to 0, another is a is equal to 1. If I am talking about Verilog HDL, I can assign both the values at the same time, but what will be the final value of a which will be considered? It is ambiguous. So, that can cause a race in your design. So, based on the language which you are using for RTL design, there is a scope for races to be introduced. So, you have to ensure the simulation you are debugging such kind of races and ensure that the design is working correctly as expected even in the presence of such kind of races. So, what are my verification goals? So, whenever I am trying to verify the RTL design, I am trying to ensure that my RTL design is fully conforming to its specifications. That is my verification goal. At the end of the day, I want to ensure my design is functioning correctly and as expected based on the requirements of the design. Now, this is the most important thing I would say in terms of verification. Remember that example which I said regarding a large processor company missing a check. This will help you to understand why that happened. Now, let us say my RTL code is good, right. I mean the design is good. I have developed my test bench in such a way that the test bench correctly verified the RTL and there are no issues on the test bench side and the design side. Now, in this case I can say it is I can sign off my design. So, I can say that the design is good, I can go to the next step which is called the tape out of the design. Now, what happens if there is a issue in the test bench? If test bench gives a false failure, then you have to debug your test bench. This is a scope where we have to debug test bench, where RTL code is good, but still the test bench caused a failure in their simulations. Now, in case if there is a bug in the RTL, what are we trying to achieve? We want the test bench to fail because we have to debug the RTL bug. So, if the RTL bug means there is a incorrect operation in the RTL which is causing the output to be incorrect for those set of stimulus or the inputs. Now, in such kind of cases my test bench will be smart to capture that failure and report it as a simulation is failing. Now, in this kind of case, I need to debug the RTL code, right. But if my test bench is showing as pass, this is the case, right. So, if you look at this section, if my test bench is showing as passing but there is a RTL bug, I will not be able to capture that bug and debug the bug. So, end of the day, this RTL is going to the next stage and it gets shipped as a product. We have to ensure that this does not happen. If you have a false failure, it will end up as a bug in your final product, right. This is the one which we have to be very careful when you are doing simulations. We have to ensure we are testing every feature of the RTL in the shortest format, in the shortest time. Now, if I look at a failing case for the test bench, now this failing case of the test bench is going to cause a test bench failure, and then there is a RTL bug as well. So, I can debug my RTL bug and kind of like should be able to identify the RTL bug and make the simulation pass. So, the things which you have to be ensure is your test bench should be smart enough to identify the failures in the RTL. If your test bench is not capturing all the scenarios, then we may end up having the bug being released to the down the ASIC design flow. Okay. So, that means we have to develop the test bench, right. So, whenever we are doing simulations, we need to ensure there is a appropriate test bench available, and there are different process of reaching the verification goals which we discussed, right. So, that the RTL is conforming to its specification. Now, what are the different phases of verification? So, the first phase, right, if you look at this thing, the first phase is build your verification environment, build your test bench environment. Once your test bench environment is ready, you can start doing the testing for your RTL design. So, in this case, I am going to apply a lot of stimulus here. If you look at this one, this is a broad spectrum verification, and we monitor with respect to coverage. Coverage means how much of testing has progressed, how much of the features of the design has been tested so far. That is the coverage which we are trying to achieve here. Now, during the broad spectrum verification, I am going to apply the lot of stimulus and get the output of the design and capture this design here. Then comes a corner case verification. See, my test bench may not be able to capture every scenario of the RTL, right. So, in case if I find that, oh, okay, this specific functionality, let us say for adder 1 and 1 inputs were not captured in my test bench, I will do a directed testing, where I directly apply A is equal to 1, B is equal to 1 and test the output of the adder to see the sum and carry. So, these are the various phases of verification. First, you will try to build your test bench environment, debug the test bench environment to ensure your test bench is ready to test the actual RTL design. Then comes the broad spectrum verification, where you apply the lot of stimulus onto your RTL design, you run this RTL design with various stimulus and capture the and ensure that all the requirements or majority of the requirements are met. If post the broad spectrum verification, if it is still not met, I will go to a directed testing, where I will be doing the corner case specific scenario. This is the part which verification engineer has to do it very dedicatedly, right. So, they have to ensure they are able to make progress on the verification, they have to ensure they are debugging the RTL design, and they have to ensure that their test bench is also ready, and kind of like help the RTL design to complete the verification phase and take it to the next steps. Now, one of the things I want to introduce in this session is the SystemVerilog language. You might be aware of hardware descriptive language like Verilog VHDLs, right, which can be used for RTL designing. But when we come to this RTL designing, the same language, if you are trying to create a test bench out, it may not have all the constructs or easier constructs. If you have any software background, there is a difference between C and C++. The difference is the OOPS concepts and the high level abstractions which you can achieve with the C++. Similar feature has been introduced by SystemVerilog. SystemVerilog is a hardware descriptive language as well as a hardware verification language. So, you can use for creating designs as well as verification. So, I want to use this opportunity to introduce the SystemVerilog. It will be very high level, but still I want you to understand how a test bench, if I have to create with SystemVerilog language, looks like. So, this is an 𝗧𝗦𝗔𝗧. 𝗧𝗦𝗔𝗧 is a committee which was formed to standardize the languages. This is because we have various tools and various methodologies and which are present in the market, and an engineer who has to develop or learn those things, if there is no consistency between or across the tools, it may cause delays in your the overall verification flow. In order to come basically reduce such kind of things, we have a committee which is called 𝗧𝗦𝗔𝗧, which standardizes the languages. This has been standardized in the year 2005, and SystemVerilog was adopted as a IEEE standard, and it was released to the users and various companies like so that they can develop tools which understands the SystemVerilog language. Now, if we recollect, right, there we have three verticals, like one is the implementation side, one is the verification side, then we had physical design and fabrications. These are the major verticals in the ASIC design flow. Apart from these things, we also have several different companies which are part of this ecosystem. Design automation, like which provides the tools, right, which provides the tools to understand and execute that code, right. So, in HDLs or HVLs. So, that is the design automation companies. For example, you have Synopsys, Cadence, you have many other design companies who provide you the tools. You have career opportunities in those design automation companies as well. You have companies which provides IPs. We discussed about IPs, intellectual property for the design. You have companies where which develop the IPs. People who are into the designer side, they can look at the IP developer roles as well. We have companies where they do something called verification IPs. These are the test bench IPs which do some protocol testing and other specific testing for verification. See, the idea here is to do the testing as soon as possible. We want to ensure that testing happens and in a reusable mechanism. If you have developed a test bench now, and then in next version of the product, if you have to again start from scratch, that may not be time effective, right. So, we want to ensure that overall the time to market that product remains good. So, we have to ensure our testing happens in a certain way that whatever test we have, a test components we have created for one of the test environment can be reused across the different environments. That kind of reusability you will see with the HVLs, which will be the SystemVerilog is one of those hardware verification language. There are other verification languages as well, but this has been most commonly used language. And then also based on the SystemVerilog, industry has come up with the methodologies. You might have heard about universal verification methodologies, which is again based on SystemVerilog. So, if you are looking at a career at verification, I would say learning SystemVerilog will be a good starting point, because it helps you to start at certain verification language and then take it to the next steps with the higher methodologies as well. Now, let us take a quick look at what is the how does the SystemVerilog test environment looks like. So, if you look at this one, right, so we have a design and a test here. This is our RTL design which we want to test it. Now, I am going to explain a SystemVerilog based environment. Really do not think too deep in at this moment to understand what are the constructs and how the mechanism actually works, but try to understand from the higher level objective only. So, we have a design which we want to test. What SystemVerilog provides is there are certain components which will generate the inputs, that we call as a generator. A generator generates the inputs which are going to be driven to the device under test or design under test. Now, how can I drive this to design and test? A generator is generating the stimulus. So, you have A is equal to 1, B is equal to 1, that gets generator. But if I have to drive it to the actual design, I will make use of another component which is called driver, and this driver will supply these inputs to the design. Generator generates some inputs and it passes on to the driver, and this driver will send those inputs to the device under test. And now, as we said, right, so we have to monitor what kind of inputs were applied, because we have to ensure that our verification goals are met. Are we making progress to meet all the requirements? Are we making progress to ensure the outputs are well verified? How can we do it? We have to monitor the input and the output of the device under test. So, on the input side, you are going to have a monitor. Similarly, on the output side, you are going to have a monitor. Now, scoreboard is a component which will compare both the inputs and outputs. We will see if there is any if there is any input and output which can be mapped and it is correct or not. So, at this scoreboard we will see all the checkers we are going to do it. Hello. Hello. Is there a question on the phone? Just give us a minute. I think we will take the question after this slide. Thank you. So, what we are going to do is we are having input and output, and both the inputs and outputs are going to be captured at a scoreboard component. Do not really understand, try to understand the scoreboard, but it is more of a component where you are trying to compare the inputs and outputs. If my input and output are matching, I am saying that yes, this specific functionality is met. And how am I going to monitor my overall progress? There will be a component which is called coverage component. So, this constitutes a entire SystemVerilog test bench environment. In SystemVerilog test bench environment, I have a generator which will generate the input stimulus. I have a driver which will apply the stimulus to the device under test or the RTL design, and then I will be monitoring the inputs and outputs and ensure my coverage of my requirements is met or not. So, that is my complete SystemVerilog test bench environment. And now what I will say is I will create different tests for different kinds of scenarios, different kinds of requirements, and this will be added into a program block. Okay. So, we will see more about how this actual flow happens, data flow happens, but at a high level this is the SystemVerilog test bench environment which you can refer to. Now, just to quickly introduce the SystemVerilog, why SystemVerilog environment, right? One thing which we understood is this is a difference between the C and C++. People who are coming from software background, it helps you with the higher level objectives. It helps you with a higher level encapsulation of your design. So, if I was to say the key building blocks of SystemVerilog is the two blocks which are available here, which is the program block and the interface. Looks like there is a question on the phone. Hello. I think question I am not able to hear, but let us take the question, all the questions maybe after a couple of slides. So, now when we are trying to introduce the two blocks here, one is a program block. See, typically in HDLs what we have is a module. When you are trying to implement a design, you will be using a Verilog module which can create the specific design, right. So, but now if I am trying to do the same thing, same test bench execution in the same module, it becomes a bit messy to kind of like differentiate between the design block and the test bench. We do not want any races to be coming in, right. So, design is, what does the design do? Design will perform certain executions on the test, on the design. Test bench will generate some vectors, but if both the things are happening in the same time, in the same delta of the time when the machine is executing the code, there could be races between the program or the test bench side and the design side. Program block helps you with a reactive region which will differentiate between the test bench execution and the design execution. And typically whenever we talking about the designs, right. So, we are talking about the signals on the design. See, whenever you are having a design, if you try to recollect a chip, right, a chip will have certain pins, right, the input pins and output pins. Any chip will have the pins. Now, if I have to apply each pin at one time, it is going to be time consuming, right. I have to understand, maybe now today's pins will be 1000, 2000 or maybe 3000 or maybe more than that. So, how can I kind of like simplify that so that developers or the designers can quickly access those pins, is by using the interface. So, SystemVerilog provides an element called interface, which is a signal, which is a collection or a bundle of the signals. So, at a higher level you can create this interface and you can just refer to that interface to refer to independent signals in that which are collected in that interface. Now, as I said, SystemVerilog programs use various object oriented programmings similar to C++ here. Now, just to quickly briefly show you, right, I mean basically how a SystemVerilog object looks like, a test bench object looks like. It gets encapsulated like this. So, you have this class packet here, and then you will be having the various elements which you want to drive on the inputs of the design. Let's say we have a memory, right? I want to access the a specific memory element. I will create a packet class. I will define the source address, the destination address of the memory, and the payload or the data which I can use it. Okay, looks like there is a call. Let's take the call once. Hello. Hello, please go ahead with the call question.
Hello.
Yes.
Hello.
Yeah, I can hear you. Please go ahead.
Sir, voice is not properly audible, sir.
I can hear you. Maybe you can complete your question.
Sir, we want to start our VLSI career, sir.
Mm-hmm.
So we want a proper guidance, sir. We are lack of guidance. We did not started yet.
So I assume you are doing your graduation, bachelor's here at
Yes,
this
sir.
moment?
We are in 4-1, sir.
Okay, okay. And
So we want to start our VLSI career. So how to start and where to start, we want to know, sir.
good question. So see, whenever we are looking at a career, first thing is we have to understand what is the skill sets needed in that career, right? So skill sets, I think, is the first step which any graduate or undergraduate can understand. What are my skill sets and how can I improve the skill sets to basically get to the VLSI job, right? Now the first thing which you want to look at is how good am I at digital designing or analog designing based on your interests. If you want to go to a career where you want to go on the digital side or the analog side, and improve the skill set on those specific two aspects, improve your digital design or improve your analog design. Now let us say I identify, let us say I want to be a digital engineer. Now look at the digital engineer and identify one of the languages to be learnt. You have these HDLs like Verilog, VHDL, SystemVerilog. Please pick one of the language and write code as much as possible. See, in case if your college does not have access to the tools, there are some open platforms available under the EDA where you can write your code and execute as well. So have an access to those. These are free of cost. So you can access those platforms to kind of like develop your HDL understanding. And if you are not able to still make progress with the open platforms because of lack of guidance there, you can also approach, maybe you can look at some internship programs at what VLSI industry provides, or you can also approach some of the intermediate companies which provides the trainings as well. So there are many companies maybe in Hyderabad or in Bangalore that perform some, they give some online guidance also, online coaching also. Enroll into those things as early as possible, and then you start developing your skills required for that the targeted domain, right. So the first thing, identify or improve your knowledge on the digital and analog side, understand the CMOS constructs and all those things. Those are part of your curriculum itself. Beyond the curriculum, start picking up one of the languages. Okay, so it could be a HDL, any Verilog, VHDL, SystemVerilog. Identify the language. If you are not able to understand the specific language, how do I learn those things? Approach the intermediaries who can help you train in those HDL languages. Okay, and then start doing the coding as much as possible. I would say that, see, if your bachelor's college is not able to provide you all the resources to become a good engineer, a good learning of those things, please do continue with your studies, go for a good college in your masters as well. It can help you, really help you to develop all those things within the college campus, right. So please understand, right, I mean, learning everything within few months is not possible. So you have to start early. Look at the third year, your third year syllabus, a lot of digital and analog concepts are there. Brush up them, approach the intermediates, work on them. If you are still not able to make progress, and please do enroll for the higher education as well, where you can get into good colleges and identify those. So hope your question is addressed. Okay. So now I am continuing with the presentation here, and now the reason we are going with a high level object based programming is it will help you with a easy mechanism to generate the test benches, generate the test inputs and apply on the design, right. So why are we doing it? Say if I have to apply each input, generate each stimulus, it will take time and I will never be able to converge on my this thing. But this higher level languages help you with the easy encapsulation of the test inputs, and then apply those inputs. What OOPS provide is the randomization. So in case of a randomization, it's a very powerful thing, similar to C random functions. Instead of generating each value, let's take the same adder example. If I have to generate A is equal to 0, B is equal to 0, A is equal to 1, let's say it's a 256 bit adder, let's say the 512 bit adder. Am I going to generate 2 power 256 or 2 power 512? It's impossible for me, right? So what I will do is, I will make use of this higher verification language, create an object and call the randomize. What randomize does is, it will automatically populate that certain inputs with the random values, which can help you with the faster closure of your verification. Okay. So this is the random functions. Let's take an example. Let's again look at the example. How does the randomization looks like it? So you have defined your object or the packet class, where you define the source address, where you define the destination address, the data. Let's say this is a memory packet, right? Now once this class is defined, you will execute this class by creating an object of this class. So you call the new on this one, it will create an object and call randomize to generate different set of interesting patterns for your simulations. So this is an example which I am just trying to show. Either you can always rely on writing each and every test input, but that's not practical. So rather you look at the higher verification languages and you apply those things. This is the thing which I want to explain, right? So in case if you are looking at a verification as a carrier, try to look at the verification carrier from the from what industry is looking for, right? The skill set which industry is looking for is higher verification languages, HDLs, like strong digital foundations. Now in this case, once I created an object, I am going to recall the randomize here, and then I will generate the set of test patterns. Now let us take the same block diagram again, right? So I want to test this DUT. Now I know there is a SystemVerilog HVL available, in which I can create some components where I can generate this class objects. That is the generator part. Generator will generate the transactions. What will the driver do? Driver will get the transactions from the generator and send it to the design. So generator is going to send the data to the driver, and the driver will pass on to the signal level of your DUT, right. Now on the design side, like I said, you have to monitor your transactions, the signal values which are getting into the design and the output of the design. So the inputs and the outputs has to be monitored for the design, and then you do the scoreboard checking. Let's say there is a Ethernet is something like it's an internet packet, right. See, whenever you are using internet, you are sending some data, isn't it? It will go to some router, and from that router it will be routed to the destination. Now how can I ensure my input to the router and output to the output of the router are same? By checking both the inputs and outputs. That is what scoreboard is doing here. It will check if the input data and the output data are as expected or not. And then if I have to say that, hey, okay, we have developed my environment, we are doing some testing, how far we are into this testing, how much is done? You create a coverage model. Coverage is nothing but where you have certain requirements mentioned, and then you start ticking the marks, right. Okay, this specific functionality design is covered in my testing, so that you do not have to revisit the same thing or redo the same thing. Okay. Now this is the environment and test which we called, right. And now where did we generate the transactions? Let us say the packet class object we created, right, which has different signal represented as variables in that, right. So I will do it in the generator. Now what will happen here? Once the generator creates an object of this class, it will be passed to the driver here. So if you look at the generator sent a transaction to the driver, and now the driver will send this transaction to the DUT. Transaction is nothing but a unit level data. Okay. So if I say at a signal level, 1 bit, 1 signal is the unit level. When I call about the test bench, it is a higher level abstraction which will capture all the inputs into one single class object, and it will pass the transaction. So here that is what we have seen, right. If you look at this design here, it will pass the design the transaction to your design, and then it will be used, the same packet will be used on the inputs and output side. Looks like there is a call on this. Hello. Hello.
Hello sir, good morning sir.
Good morning.
సార్ నా పేరు లక్ష్మీదేవి సార్, మా బాబు కోసం మాట్లాడుతున్నాను సార్.
చెప్పండి.
సార్ మా బాబు బీటెక్ చేసినాడు సార్. తను మెకానికల్ డిప్లొమా బీటెక్ రెండు అయినాయి సార్. అయితే అందులో ఒక సబ్జెక్ట్ ఫెయిల్ అయినాడు సార్. మరి మా బాబు కరోనా టైంలో ఫెయిల్ అయినాడు సార్. మరి తనకు వేరే ఇట్లాంటి ఏమైనా అవకాశాలు ఉంటాయా సార్? తను వేరే కూడా చేసినాడు సార్, 24/7 అందులో చేసిండు, ఒకటి ఐటీఐలో చేసిండు, తర్వాత హెచ్డిఎఫ్సిలో చేసిండు.
ఓకే, సో
ఇట్లాంటి పిల్లలకి ఏమైనా అవకాశాలు ఉంటాయా సార్?
లక్ష్మీదేవి గారు, అంటే కోర్స్ కంప్లీట్ చేస్తానికి అవకాశం ఉందని ఒకసారి కాలేజ్ని సంప్రదిస్తే బాగుంటుంది కదండి. ఫస్ట్ మీరు కాలేజ్తో మాట్లాడచ్చు, ఆ కోర్స్ కంప్లీట్ చేయగలుగుతున్నారా లేదా. ఒకవేళ కోర్స్ చేయలేకపోతున్నారంటే ఇండస్ట్రీకి కావాల్సిన కోర్సెస్ కూడా చేయొచ్చండి బయట. ఇప్పుడు ఇండస్ట్రీలో మీకు లెట్స్ మీ డిప్లొమా బేస్డ్ మీద అంటున్నారు కాబట్టి ఇండస్ట్రీలో మీరు కావాల్సిన కోర్సెస్ మీరు చేస్తే దానికి తగ్గట్టుగా మీకు జాబ్స్ వచ్చే అవకాశం ఉంటుంది. ఇప్పుడు VLSI ఫీల్డ్ అనేది ఒక చాలా టెక్నికల్ ఫీల్డ్. ఇక్కడ ఎలక్ట్రానిక్స్ రిలేటెడ్ బ్యాక్గ్రౌండ్ అడుగుతారు. ఒకవేళ మీ బాబుకి ఎలక్ట్రానిక్స్ సైడ్ ఇంట్రెస్ట్ ఉంటే ఈ VLSI ఫీల్డ్ నేర్పించే కొన్ని కంపెనీస్ ఉంటాయి. ఆ కంపెనీస్ని మీరు అందుబాటులో తీసుకొని మీరు కోర్సులు నేర్చుకోవచ్చు. లేదంటే మీరు ఇంకొక ఏంటంటే మీరు సాఫ్ట్వేర్ సైడ్ వెళ్దాం అనుకుంటే సాఫ్ట్వేర్ కావాల్సింది మీరు నేర్చుకోవచ్చు. అంటే ఇప్పుడు మీకు సాఫ్ట్వేర్ కావాల్సింది స్కిల్ ఇంపార్టెంట్ అండి. డెఫినెట్గా అన్ని కంపెనీస్ ఒక బేసిక్ రిక్వైర్మెంట్ చెప్తారు, మాకు గ్రాడ్యుయేట్సే కావాలి అని. సో నా ఉద్దేశంలో గ్రాడ్యుయేషన్ చేసుకొని కంప్లీట్ చేసి మీరు ఈ ఇండస్ట్రీ కావాల్సిన కోర్సెస్ చేయటం బెటర్ అండి. లేదంటే మెకానికల్ సైడ్లో మీరు ఒకవేళ డిప్లొమా బేస్డ్ మీద మీకు ఏమైనా అవైలబిలిటీ ఉంటే అది మీరు మెకానికల్ సంబంధించిన వాళ్ళని సంప్రదిస్తే వాళ్ళు చెప్పగలుగుతారండి. ఓకే, so continuing with this, right, so here once we have the packets which are available and then these packets are getting monitored from both the input side and the output side, then we will be doing some checking for the packets are matching or not. This is very essential when we are talking about verification. How are we going to match the inputs and outputs, and how are we going to track my verification progress? Okay, so like we are going through the coverage, we are looking at overall how much of my testing has been covered. Is my testing or the verification complete for this or not? If there are some certain scenarios which are not getting covered in this specific scenario, can I do some director level testing and perform those testings? Okay. Okay, so having looked at simulation, right, so far we are looking at what is a register transfer level simulation. Now this happens at a higher level language, like you have a design which you have created or which was available to you in Verilog or VHDL design, and then once this design is available, you perform that RTL level verification by doing the simulation. But how am I going to do the same thing once the synthesis is done? See, synthesis is the stage which will convert your higher level language into the gates, right, the basic gates and those things. That is the gate level simulation which we are going to talk about here. So in case of gate level simulation, we are mainly referring to the basic gates, right. So like you are having NAND, NORs, multiplexers, all this gate representation is used here. So if you look at this diagram here, right, so this is a gate level representation of your RTL design. So once your RTL design is available, you are going to perform a gate level simulations to ensure if my gate level netlist is also doing the same functional aspects as was my input RTL design, right. See, the thing is, whenever we are trying to rely on tools to convert, right, from the higher level language to let's say some gates or netlists, how can I ensure that it is doing the same job? See, any tool can have issues, right, or maybe the libraries which are using to model the netlist, that can have issues. So if you want to do some sort of testing, you have to do a verification at every stage whenever there is a data progression or the design changes happening. So in this case, I am going to do a gate level simulation as well. So what is a gate level simulation? It's a verification of your netlist with the, either you can use the same RTL test bench or you can use a gate level required inputs there. Now, the important aspect of the gate level simulation is here you can accurately specify the delays associated with each nets. So, if I have any zero delays, see basically what is zero delay simulation, where I am saying is an ideal world. So, I have gates here, I have wires which are connecting each gate, one gate to another gate. Now, how can I if I say that there is no delay between these things, that is an ideal world. Now, I can perform zero delay simulation, which is a fast gate level simulations, but in order to test something like a closer to a real design, I want to say how much is the delay between each one gate to another gate. That you can specify in the gate level simulation by using the SDF as well. SDF stands for standard delay format. It is the timing model of your design, which will say how much lag or how much delay this wire or net is introducing, and how much propagation delay this specific gate is introducing as well. Now, like I said, either you can use the existing RTL test bench and perform the gate level simulation, or what I can do is there are some special tools or special what we call as a pattern generators, through which we can apply the stimulus also for the gate level netlist. And mind you, I mean the question can be, hey, why should I invest on learning Verilog when I know the functionality of gates, I can directly connect the gates, but practically the gates gets multifold, right? So you can never be able to achieve everything into your gate level simulation at the same time. Okay, so that's the reason the simulation time and debug cycles can be very long in terms of gate level simulation. Looks like that. Let's take a call here. Hello.
Hello.
Yeah, please go ahead.
Hello, sir.
Yes, please go ahead. Yes, I can hear you.
సార్ VLSI పైన మాస్టర్స్ చేయడం కానీ లేదంటే ఏదైనా అబ్రాడ్ వెళ్ళి హైయర్ స్టడీస్ చేయడం వల్ల ఏదైనా యూజ్ ఉంటుందా?
డెఫినెట్గా యూజ్ ఉంటుందండి. ఎందుకంటే మీరు మీరు ఎక్కడైతే మీరు గ్రాడ్యుయేషన్ చేస్తున్నారో, ఒకవేళ మీకు సంబంధించిన లాంగ్వేజెస్ అన్న మేబీ కేస్ స్టడీస్ అన్న మీరు పర్ఫెక్ట్గా చేయకపోతే, ఇండస్ట్రీకి కావాల్సింది ఏంటంటే ఆ లాంగ్వేజెస్లో మీకు ఎంత పట్టు ఉందనేది. లాంగ్వేజెస్ అంటే మీకు ఓకే, లాంగ్వేజ్ కన్స్ట్రక్ట్స్ నేర్చుకోవటం కాదండి, లాంగ్వేజ్ ఎలా యూజ్ చేయగలుగుతున్నాము ఒక ప్రాక్టికల్ సినారియోలో, అది మీకు హ్యాండ్స్ ఆన్ ఎక్స్పీరియన్స్ అంటారు దాన్ని. మీరు ఎక్కువగా ఒక డెవలప్మెంట్ చేసి వెరిఫికేషన్ చేస్తే మీకు ఆ హ్యాండ్స్ ఆన్ ఎక్స్పీరియన్స్ వస్తుంది. ప్రతిదీ మీరు చదువుకునేది బుక్లో ఉండకపోవచ్చు, మీరు ఒకసారి ఆ కోడ్ రాసి రన్ చేస్తే అది ఎగ్జిక్యూట్ చేసేటప్పుడు మీకు ఎర్రర్స్ వస్తాయి, కంపైల్ చేస్తారు, సిమ్యులేట్ చేస్తారు, అలాంటివన్నీ నేర్చుకోవాలి మీరు. మీకు ఒకవేళ అవన్నీ బీటెక్లో మీరు ఒకవేళ మీకు అందుబాటులో లేకపోతే మీరు డెఫినెట్గా మీరు మాస్టర్స్కి వెళ్తే చాలా మంచిది. మీకు అబ్రాడ్ అయినా మాస్టర్స్ బాగుంటుందండి, మన ఇండియాలో కూడా మాస్టర్స్ చాలా బాగుండే కోర్సెస్, చాలా మంచి మంచి కాలేజెస్ ఉన్నాయి, ఐఐటీస్ ఉన్నాయి, IIITs ఉన్నాయి, NITs ఉన్నాయి మనకి. సో మీరు టాప్ కాలేజెస్లో మీరు ఒకవేళ మీరు తెప్పించుకోగలిగితే మీరు, ఆర్ లాట్ ఆఫ్ ఆటోనమస్ కాలేజెస్ ఉండే ఎక్కడైతే VLSI ఫోకస్ బాగుంటుందో వాటిని ఐడెంటిఫై చేసి మీరు మీ స్కిల్ సెట్ని పెంచుకోవడం చాలా ఇంపార్టెంట్ అండి. ఎందుకంటే
ఎంప్లాయ్మెంట్ వైజ్ చూసుకుంటే ఇండియాలో అంత ఇదిగా అయితే లేదు కదా సార్. ఐ మీన్ అంత ఎంప్లాయ్మెంట్ కల్పించే అంత రీసోర్సెస్ అయితే లేవు కదా సార్ ఇండియాలో.
మీరు VLSI గురించి మాట్లాడితే ఇప్పుడు VLSI ఇండస్ట్రీ వన్ ఆఫ్ ద లీడింగ్ ఇండస్ట్రీస్ అండి. ఇక్కడ పేస్ అన్న ఆపర్చునిటీస్ అన్న చాలా బాగుండే. ఇప్పుడు మీరు నంబర్ ఆఫ్ ప్రతి ఇండస్ట్రీలో ఒక అప్ ట్రెండ్ డౌన్ ట్రెండ్ ఉంటుంది. బట్ మీరు ఒకవేళ ఆ టైంలో మీకు జాబ్ ఆపర్చునిటీస్ రాకపోతే మీరు డెఫినెట్గా హైయర్ స్టడీస్ చేస్తే ఇక్కడ మంచి ఆపర్చునిటీస్ ఉన్నాయి, మంచి కాలేజ్లో చేస్తే మంచి ఆపర్చునిటీస్ ఉన్నాయి. సో మీకు ఎంతైతే అబ్రాడ్లో ఆపర్చునిటీస్ ఉన్నాయి అనుకుంటున్నారో ఇక్కడ కూడా చాలా ఆపర్చునిటీస్ ఉన్నాయి. ఇంకొక అడ్వాంటేజ్ ఇక్కడ ఏంటంటే మీరు ఒకవేళ చూస్తే చాలా వరకు వర్క్ అనేది బయట ప్రీవియస్గా యూఎస్లో ఒక డెవలప్మెంట్ జరిగేది, ఇప్పుడు అది ఆఫ్ షోర్ అంటే ఇండియా సైట్స్కి వస్తున్నాయి. ఇప్పుడు మీరు పెద్ద మేజర్ కంపెనీస్ ఉంటాయి, ఇంటెల్, శాంసంగ్, క్వాల్కామ్, రైట్, ఐ మీన్ ఆర్ బ్రాడ్కామ్, AMD, ప్రతి డిజైన్ కంపెనీ మన హైదరాబాద్లో కూడా ఉన్నాయి, రైట్. సో అలాంటి ఆపర్చునిటీస్ ఉన్నప్పుడు మనం ఒకవేళ ఆ స్కిల్ సెట్కి తగ్గట్టుగా మనం రెడీ అవుతే డెఫినెట్గా ఆప్షన్స్ ఉంటాయండి. ఇక్కడ ఓన్లీ అబ్రాడ్లో ఆప్షన్స్ ఉంటాయి అనేది అంటే 100% నేను చెప్పను, బట్ డెఫినెట్గా మనకి ఇక్కడ వెరీ గుడ్ ఆపర్చునిటీస్ ఉన్నాయి. ఇన్ఫ్యాక్ట్ నేను పర్సనల్గా నేను ట్రిపేటీలో చేశాను, దాని తర్వాత నేను కంపెనీలో ఉన్నాను. వెరీ గుడ్ ఆపర్చునిటీస్. ఐ థింక్ నేను లాస్ట్ 18 years నుంచి అదే కంపెనీలో పనిచేస్తున్నాను. సో ఇట్స్ గ్రోత్ అన్న చాలా బాగుంటుందండి. ఐ థింక్ డెఫినెట్గా పేస్ ఆర్ ఆల్సో చాలా వెరీ గుడ్ హియర్. ఓకే, సో నౌ లెట్స్ కంటిన్యూ విత్ with our agenda, right? So far we have looked at what is meant by RTL verification. RTL verification is where you are performing your register transfer level designs verification. You are trying to ensure your design is conforming to a specification. How are you going to verify it? There are various techniques. మనం చూసిన టెక్నిక్స్ ఏంటంటే, ఫస్ట్ థింగ్ ఇస్ సిమ్యులేషన్ టెక్నిక్స్. సిమ్యులేషన్లో మనం టెస్ట్ బెంచ్ క్రియేట్ చేస్తాము. ఆ టెస్ట్ బెంచ్ will apply the various inputs to your design and then you will monitor the outputs. If you want to build a career in the simulation side, you should learn one of the verification languages or get really expertise in Verilog and SystemVerilog maybe, right? And then comes gate level simulation. In gate level simulation, what we are trying to do, once we had the input design synthesized as a netlist, we want to ensure that netlist is doing the same job as the input RTL design. That's the gate level simulation. In case of gate level simulation, we try to achieve the simulation correctness or design correctness post netlist generation. So that's the simulation techniques we have looked at it. Now let's look at what is meant by formal verification. See, so far మనం చూసింది ఏంటంటే, ఇక్కడ what we had is a test bench has to be created, right? So you have to invest a lot of time in creating a test bench and then simulating the design. So there are various phases of verification. Simulation is important. I am not saying simulation is, we can go do away with simulation and start doing formal and static verification. What I am saying, simulation is important because it gives you all the different test scenarios which you can execute, and with the cost of the simulation could be very small as well, right? But when it comes to finding hard corner case bugs, or where you want to develop or do the testing without even before the test bench has started, that's where formal and static verification come into the picture. Now let's look at what is the formal verification. See, formal verification comes post, again the RTL design itself is available. So you can say that it comes after the logic synthesis, because formal can be applied on the netlist as well as the RTL itself. So what happens in formal verification? This is the flow for formal verification. So we have this RTL. There is a synthesis tool which generates the netlist. Once the netlist is generated here, we want to ensure our input RTL design and the netlist both are equivalent. See, whenever there is a design transformation happening, we have to ensure both the input design and the netlist is equivalent. See, when we had an adder, the RTL code of the adder could be as simple as assign out is equal to, or sum is equal to A and B, or A XOR B, right? That's my adder functionality. If I have to define my carry will be carry is equal to A and B. So, but when I synthesize this, it will represent that in a gate level form. Like I will be having certain NAND gate implementations or maybe OR gate implementations, I will be having gate level forms. How can I ensure this adder which got generated by netlist is the same as the simulation before the simulation, the RTL design? That can be done by formal verification. Formal verification helps you to do equivalence checking in so that you can say that the two versions of the design are functionally equivalent or not. That's one of the aspects of formal verification. Now if you don't have the formal verification, what will happen is you have to do a lot of test bench development time. While the test bench is developing, you can still capture a lot of bugs by using formal verification. If you have a netlist available, or you can apply the formal verification on the RTL design itself. So that way formal verification is gaining a lot of traction now in the industry, and formal verification uses some sort of a mathematical modeling. They use mathematical modeling to prove these two designs are equivalent or not, or they use mathematical functionalities to ensure the functional correctness of the design is met or not. So this is very important in terms of verifying without test bench. This is one of the things where many of the leading companies are focusing now. Formal verification is one of the, I would say that in next few years, formal verification, if you are looking at verification as a career, formal and static verification are equally important as simulations. Okay. So that's a formal verification. So in case of a formal verification, we use mathematical models to prove the two versions of the design are equivalent. And also, let's say my RTL design, you're doing some bug fixes into your RTL design. You found some issues, RTL designer is going to do some bug fixes in that. Now, how can I say that the reference design A, what is my golden design so far, which I believed it was correct, but once I found the design bug, I fixed the design. So the design version has changed, right? So now I have two versions of the design. Now, how can I say that the rest of the functionality is matching? So formal verification can help you to match or map the majority of the functionalities as well, so that you can say, oh, okay, this new design which has the bug fixes is fully formally verified, and I can make this design as a golden design for the subsequent steps. So in that way, formal verification helps you with a lot of equivalence checking, property verification, data path verification as well. Okay. So having looked at formal verification, there is another area where you can verify your RTL design without any test bench. So that's called static verification. So see, typically static verification happens in parallel to majority of these verification techniques. You can perform the static verification while you are doing the simulation, while you are doing the synthesis, while you are doing the implementation as well. So that way static verification has gained a lot of traction in last few years. So what is static verification? So let's understand what is the traditional design flow first. In case of a traditional design flow, you are going to design certain specific blocks of your entire SOC. Okay, before we get started, let's take a call here. Hello. Hello.
Hello, sir.
Yes, I can hear you. Please go ahead.
సార్ ఇప్పుడు మేము 4-1 కరెంట్లీ 4-1 లో ఉన్నాం సార్ ఈసీ ఫీల్డ్.
చెప్పండి.
సో నెక్స్ట్ VLSI ఫీల్డ్ లోకి వెళ్ళాలనుకుంటున్నాము. సో ఇంటర్న్షిప్స్ 4-1 లో చేస్తే బాగుంటాయి కదా, ఏ ప్లాట్ఫామ్స్ లో చేస్తే కొంచెం యూజ్ ఉంటుంది చెప్తారా?
యా డెఫినెట్లీ. సో లైక్ ఇంతకు ముందు చెప్పినట్టుగా మీరు ఒక స్కిల్ సెట్ మీరు డెఫినెట్గా స్ట్రాంగ్ ఉండాలి. లెట్స్ సే డిజిటల్ డిజైన్ ఉంది, స్ట్రాంగ్ ఉండండి డిజిటల్ డిజైన్ ఆర్ అనలాగ్ డిజైన్లో మీ ఇంట్రెస్ట్ బట్టి. అండ్ మీకు ఒకవేళ మీ కాలేజ్ నుంచి మీరు 4-1 స్టడీస్తో పాటు మీరు ఇంటర్న్షిప్ చేయగలుగుతున్నారు అనుకుంటే, ఇంటర్న్షిప్ చేసేటప్పుడు ఎక్కడైతే ఎక్కువ ఆపర్చునిటీస్ ఉన్నాయో. హలో, వినపడుతుందండి? ఓకే. సో మీరు ఎక్కడైతే ఆపర్చునిటీస్ ఉంటాయో అది మీరు పికప్ చేసుకోండి. లెట్స్ సే వెరిఫికేషన్. ఓకే, సో ఐమ్ గోయింగ్ టు కంప్లీట్ దిస్ ఆన్సర్. సో మీరు ఏం చేయండి అంటే, ఎప్పుడైనా మీకు వెరిఫికేషన్ సైడ్లో ఒకవేళ ఎక్కువ ఆపర్చునిటీస్ ఉంటాయి, టిపికల్గా మీరు ఒకవేళ రేషియో చూస్తే మేబీ 60% వెరిఫికేషన్ జాబ్స్ ఉంటాయి, మేబీ 20% డిజైన్ ఉంటాయి, అండ్ మేబీ ద అదర్ రెస్ట్ ఆఫ్ ద జాబ్స్ మేబీ ఒక 20% అట్లా ఉంటాయి. సో వెరిఫికేషన్ ఫీల్డ్, వెరిఫికేషన్ ఇంజనీర్స్ ఎక్కువ మంది అవసరం ఉంటారు ఇండస్ట్రీలో, ఎందుకంటే వెరిఫికేషన్ చాలా కాంప్లెక్స్ ఉంటుంది. లాట్ ఆఫ్ థింగ్స్ మాన్యువల్గా చేయాలి, ప్లస్ టూల్స్ యూజ్ చేయాలి, ప్లస్ చాలా వేరియస్ థింగ్స్. మోర్ దాన్ ద డిజైనర్, వెరిఫికేషన్ రోల్స్ మీకు ఎక్కువగా ఆపర్చునిటీస్ ఉంటాయి. సో మీరు వెరిఫికేషన్కి సంబంధించిన ఇంటర్న్షిప్స్లో మీరు అప్లై చేసుకోవటం బెటర్గా ఉంటుంది. ఒకవేళ వెరిఫికేషన్ సైడ్లో వెళ్ళాలి, లేదు నేను డిజైన్ సైడ్లోనే వెళ్ళాలి అనుకుంటే, స్ట్రాంగ్ HDL లాంగ్వేజ్ ఉండండి, స్ట్రాంగ్ డిజిటల్ స్కిల్ సెట్ పెంచుకోండి, అండ్ 4-1లో డెఫినెట్గా అప్లై చేయండి. సో దట్ మీరు మీ గ్రాడ్యుయేషన్ అయ్యే లోపల ఒక 1 year ఇంటర్న్షిప్ విల్ బి రియలీ హెల్ప్ఫుల్ ఫర్ యూ టు మేక్ ద కెరియర్ ఇన్ దాట్. సో వన్స్ అగైన్ ఐమ్ సెయింగ్, మీరు ఒకవేళ డిజైన్ ఆర్ వెరిఫికేషన్ సైడ్ వెళ్ళాలనుకుంటే మీ స్కిల్ సెట్ దానికి తగ్గట్టుగా పెంచుకోండి. డిజిటల్ సర్క్యూట్స్, అనలాగ్ సర్క్యూట్స్, బేస్డ్ ఆన్ మీ డిజిటల్ అనలాగ్ వెళ్దాం అనుకుంటున్నారు, వాటిలో స్ట్రాంగ్ ఫౌండేషన్స్ పెంచుకోండి. దాని తర్వాత ఒక HDL లాంగ్వేజ్ పెంచుకోండి. మీకు ఒకవేళ ఇంటర్న్షిప్ ఆపర్చునిటీస్ వస్తే, ఏ ఇంటర్న్షిప్ ఆపర్చునిటీ వచ్చినా VLSI ఫీల్డ్లో డెఫినెట్గా తీసుకోండి. బికాస్ ఎనీథింగ్ యు ఆర్ లెర్నింగ్ న్యూ ఈజ్ ఆల్వేస్ గోయింగ్ టు హెల్ప్ యూ టు బిల్డ్ యువర్ స్కిల్ సెట్. సో దానికి తగ్గట్టుగా మీరు ఒకసారి మీ టూల్స్ యాక్సెస్ అని అది వస్తే లాట్ ఆఫ్ ఎక్స్పెరిమెంట్స్ చేయండి, స్మాల్ బాక్స్ ప్రిపేర్ చేయండి, వాటిని వెరిఫై చేయండి. ఆర్ EDA ఓపెన్ ప్లాట్ఫామ్స్లో కూడా యూజ్ చేసుకోవచ్చు. చాలా అంటే కొన్ని ఓపెన్ ప్లాట్ఫామ్స్ ఉండి అక్కడ మీరు డైరెక్ట్గా టూల్ యాక్సెస్ ఉంటుంది, అది మీరు యూజ్ చేసుకోవచ్చు. Okay, so now switching back to our static verification, right? See, whenever we are developing certain RTL designs, we always start small. We identify the small design blocks and we try to integrate those design blocks to create a entire design. So what are we trying to do? We have identified some blocks, and these blocks sometimes there could be some pre-existing protocols. Let's say there is a memory protocol. right? Whenever you have a mobile, right? So you have a memory component in that, and if processor has to communicate to that memory, there is a predefined protocol. Now every time you don't have to design the same, because there is an existing IP or intellectual property of that block which you can directly pick it and use it in your design, right? So when you are connecting the processor and the memory block. Now there are existing IPs which are going to do the IP integration. Once IP integration is successful, when the testing is done, you go to the implementation state where you do the synthesis and place and route. That is a traditional flow. I have the IPs, I will integrate the IPs. Once the integration is done, I will go for synthesis and place and route to create the actual schematics which can be used for the masking. Now that's a static, that's a default flow. What happens in static verification? When you have static verification, lot of these checks which happens in the implementation, that you can get it upfront during the initial phase itself. So basically different engineers may be using different coding styles. Like I said previously, see, some coding styles may be okay during the simulation or the initial design phase, but when it comes to the actual implementation, this may not be synthesizable. Means the input design which you are giving, it may not generate the netlist at all, or it may generate incorrect netlist which you are not expecting. Maybe you are expecting a flop or a register, and it ended up generating a combinational logic. So that means there is an issue because of your coding style or the constructs which you are used, which is getting exposed very late in the cycle. So how can I get this late bugs caught early during the design cycle? That's what you can achieve with the static verification. In case of static verification, what it provides is various mechanisms to do this constructs based checks as well. So you have lints. Lint means whatever code you are trying to write, it will parse each line of the code, understand the constructs, and say if your code is a good code or not, a clean RTL or not. That's the lint. Now let's again take the same mobile SoC. See, in mobile SoC you have memory, you have processor, you have different IO communications, right? Because it has to communicate with maybe a 5G module or a 4G module. So different modules will have different clock speeds, and that means you are having different portions of the design with different clock frequencies. So how can you do the testing in simulation with clock frequency? You may not, right, unless you have some delays. So when you are traversing from one clock frequency to another clock frequency, there is a possibility of data loss or synchronization issues. If you want to catch such kind of clock domain crossings, you can use static verification, which can help you to identify such kind of clock domain crossings. So that's the advantage with static verification, which can help you to do what we call as sign off. Sign off is where we say the RTL is good, RTL is clean. That's the sign off which you can achieve right up front during the early design phases itself, instead of going to the implementation. When the implementation has an issue, again you go back to the initial design. That is a time consuming process. But if I can catch such kind of implementation issues upfront during the RTL design, it can help to speed up my verification process, and it can help you to deliver that product to the end user in faster way. So what happens in lint methodology? Like I mentioned, right? So lint methodology works on the coding, right? So when you are trying to code certain Verilog, or maybe some HDL language, you are going to write in certain format. There will be syntax, a known syntax or LRM syntax which you will be using to code the design. That syntax or the constructs which you are using may not be synthesizable or may not be correct or accurate sometimes. So because see, one designer may not be doing it, one expert may not be doing it. There may be hundreds of designers or maybe tens of designers who will be developing that code. Now when they are developing that code, there could be many syntax or lint issues because there may not be common terminologies used by every designer. So if you have to ensure your design is clean, you can perform the lint checking, which can help you to understand if the constructs are legal constructs, are synthesizable constructs, are structurally are good or not, and then we can ensure my RTL is clean right up front, so that I can take it to the next steps. That's the lint methodology. Okay, let's take a call here. Hello.
Hello. Good morning, sir.
Yeah, good morning. Please.
My name is Sukanya, sir. I am calling from Warangal.
Hey, Sukanya.
My question is, sir, how to handle continuous changes in design during the verification phase, sir?
Yeah, so when you say continuous changes in the design, you mean to say, do you mean to say the design is developing?
Yes, sir.
Okay. See, when the design is developing, you should be actually targeting more on the static kind of verifications, right. See, if you want to simulate that design, an incomplete design, you have to black box those changes for which the test bench is not complete. But if you have a test bench which is complete and the RTL which is getting upgraded with the newer components, you have to ensure test bench is also upgrading to test those features, right. Otherwise, you can use the static verification to fully validate or to fully verify those new components with a new code which gets added as well. Does it answer your question?
Yes.
Right. So, see, whenever there is a design progression, you always go back to see if the new code is added or not. So, you cannot rely on the same test bench. So, you have to ensure the new tests are added which checks those designs, the new constructs of the design. If that does not happen, there is a mismatch, right. So, you are not fully verifying that new code which gets added, and that is where the coverage actually come into a picture. When you have new code, there are some let us say there is a code coverage. What does code coverage do? It will do various coverage checks, like a line code coverage or a toggle code coverage, right, or a branch or conditional code, which will help you to understand if this new code which was added was covered in my testing while doing the testing also or not. So, you enable your code coverages, you enable the functional coverage on the test bench side to ensure the testing happens for those new code happen. Okay. So, let us continue, right. Like I said, see, whenever we are talking about a large SOCs, the different blocks of those SOCs we may have different clock domains, right. When I say clock domains, the operational frequency of that design block may be different from the system clock. See, everything cannot work or may not be work at the same clock frequency. Why do we have a clock in a design? Because we want to progress the design, right, through some time units or through some simulation or through some different clock edges. We want to apply different tests that will help you with the protocol also. When you are having a master clock which is the overall system clock, every component of the design may not be functioning because some components may have larger propagation delays. It may need more slower clocks to completely process the data. So, that means different portions of the design may have different clocks, which are now we want to verify these different clock domains. We want to ensure our data is able to progress from one clock domain to another clock domain and it is able to synchronize. So, how can we achieve that? By using clock domain crossings. These are the issues which you can observe in terms of the cross domain crossings. One is the metastability. What happens? Let us say there are two flops here and each of these flops has two different clocks. Now, if there is no synchronizer between the two clocks, it is possible that while the clock B is coming in, the data on output of the first flop, right, flop 1 may not be stable. So, that means you are sampling for the flop 2 at a point when the A is not stable. So, this can cause erroneous outputs as well. That is the metastability. Another clock domain bug is glitches. See, every element in your design has certain propagation delay. So, let us say in this design path, right, from A to B, there will be a propagation delay which will be different from A to C because of the number of gates in between. Now, that may cause glitch on the output D because both the data B and C are not available at the same time. They may be transient between that time and that cause a glitch on the output. So, by using CDC or clock domain crossing of static verification, we can identify such combinational blocks where a glitches can be introduced. Similarly, there could be issue with the reconvergence. See, with reconvergence is you sampled some flops, you sampled some data, again the reset or the data again goes back and again comes back to the same point. That is a reconvergence. Again the same transient issues can be observed in the design, which can later affect in your while during the simulation, while during the implementations or the actual product. There may be mismatch between the original RTL design behavior versus the final implemented design behavior. Those kind of issues you can catch by using the CDCs here. Similarly, like clock, you can do the reset synchronization as well. When you are applying the reset is what? Reset is when you are trying to say certain block is resetted, because see, whenever we switch on your mobile phone, let us say, right. So, you are switching on your mobile phone, if there is no reset, your display could be doing something, your memory could be doing something, your 5G network may not be on or 4G network may not be on, different blocks of your design will be at different state. How can you ensure all the blocks are at the same state? By applying the reset. Reset is when you say all the outputs or inputs should be a known value, there shouldn't be any unknown value. But if there is issue between the number of gates or number of flops, synchronized circuits between the different blocks of your design, that can cause the reset synchronization issue and your device may not be resetted correctly. So such kind of issues where you want to statically, without doing any test bench, without applying any test bench, if you want to catch these bugs, the static verification with CDC can help you there. Okay. So far we have looked at the, I think the two major components on the simulation side, which is the RTL dynamic simulation and gate level simulation, which happens on the net list. If I don't have test bench, we can still do the verification techniques by using formal and static verification techniques. So these are the four major techniques at which can be used at a block level, IP level, maybe depending upon the complexity of the block, you can be doing these testings at various levels. Okay. Now let's understand, if I go from so far how are we defining this, where should we use which verification technique? Okay, I think we have a call here. Hello.
Sir, good morning, sir.
Morning. Yeah.
Sir, I am Chandrasekhar from Hyderabad, sir.
Hey, Chandrasekhar.
Sir, I completed my BTech, sir.
Okay.
Hello.
Yes, Chandrasekhar, please go ahead.
Yeah.
I can hear
sir,
you.
Sir, actually, I have a question, sir. So, as a fresher, I just want to know what is the important questions to face the technical round of interview after completing all round and the final round. I am asking, sir, technical questions.
So you're saying what kind of questions are asked for VLSI based companies?
Yeah, final round of.
Final round means I didn't understand. I mean the initial round
Yes,
and final round.
Technical come HR round like that, sir.
Oh, okay.
So
Okay.
as a fresher,
Yeah. Typically, industries start by there is a screening round, what we call is a screening round, because see, the number of applications may be high, and there could be screening round which could be either a written test or a screening round of interview. Okay. In that round, you will be judged for the basic understanding of the majority of the things. You could be asked questions in the digital domain or the analog domain based on the company where you are applying the job, or you can be asked question in the skill sets which are needed for the job, right. So whenever you are trying to apply a job,
sure,
look at the job role, right. Look at what kind of skill sets they are asking for and prepare yourself for those skill sets. Let us say there is a verification engineer job role. Now when you look at the verification engineer job role, they will say that understanding of Verilog is must. So that means that you must focus on that skill set to ensure you have covered the Verilog language well. Digital design concepts are must, or analog design concepts are must, right, or a high level understanding of advanced Verilog concepts or maybe advanced design concepts or maybe CMOS or fabrication concepts. Look at the job profile first. All the questions whatever you receive are going to be based on the job role, and ensure that wherever you are applying you do understand which company, what is the background of the company, and what is the job role for which you are applying the job. And once you understand the skill set, there will be first round of screening or maybe a written test where you will be asked questions in those domains itself, and then it goes to the technical rounds. So technical rounds is the where we evaluate a candidate for those specific skill sets and if they are able to meet the requirements of the job, right. This could be a more advanced interview questions. The questions typically are on the how the industry pursues a certain technology. You see everybody knows what is the AND gate output, right. So you know that how the AND gate, but the questions may be asked for you to design, let us say, a 4-bit adder or a 4-bit adder using multiplexers. So you should be able to explain by using various digital concepts on these problems, right. So I think the most important aspect will be the solutions. Can you come to a solution for a specific problem? So that you should be able to apply it by learning or reading more and more, and actually practically applying those things either on the digital side or through some HDLs. Do that level things where depending upon the job role requirements, and post the technical round. Typically the HR round happens where your compatibility, your communication skills are meeting the requirements for that job role or not. So those will be, I would say, the 3 rounds typically, and the technical rounds could be multiple technical rounds depending upon the job role where you are applying and depending upon the fields which are encompassed into that job role. So you may have requirement for digital design, analog circuits, CMOS, fabrication, or maybe it could be for with respect to some HTLs only, right. So based on that job role, please prepare yourself. Okay. So, so far what we are trying to achieve is, maybe we can take a small example here, right. So let's say we have a simple adder, right. So when we are talking about adder, we have 2 inputs, there is a sum and carry outputs, we have the adder functionality, we have validated that adder functionality by or verified the adder functionality. Now this adder goes into an ALU block, like arithmetic and logic unit, which is the numerical unit where you perform the operations. Once you have this arithmetic and logic unit available, that is a higher level design. Now you go for the next is a processor, and this ALU blocks gets incorporated in the processor, and your processor block has other blocks as well, and this processor comes out as a mobile SoC, where this one of this component is a processor, and you have several other chips which are needed for a mobile, maybe a 5G unit, or could be a memory unit outside this thing, right. So we can always have some external memories, right. If you look at, if you try to visualize your mobile, right. So you have these things. So but the question here is, how can I validate the entire SoC right at the RTL? See, I do not want to get the processor, memory, everything available as a product, and then I start doing the validation. That will be very late. And what if there is an issue while connecting all these things and there is some issue in that, I cannot go back and it will be very costly affair. Remember that example where the bug was introduced when it went to the actual product? How can we avoid those things right upfront during the RTL designing itself, or maybe RTL verification itself? That is called as SoC level verification. SoC stands for system on chip. The complete chip or the complete system is available on one single chip with multiple dies available, which you can validate right upfront during the simulation, right upfront during the design and verification cycles. That is the SoC design and verification flow. That is what we are going to take it in the next section. So the most important aspect of a VLSI is, I would say, PPA. P stands for power, next P stands for performance and area. Power, performance, area. Remember, these 3 are the most essential items of any VLSI product, and if you master this in any of the flows, this is a expert level or architect levels things which you can basically the entire career of the VLSI is on to this. How do I define my power? You have a mobile. Do you want your mobile to consume more power or less power? It is always less power, right. You want your mobile to be operated for longer times, right? The battery shouldn't drain out. Means any application of VLSI, we want the power to be less. What about performance? We want our mobile to perform much better, right. Our laptop should perform much better. The newer version of the laptop should perform better than the previous version, right. So the performance of my product should increase, right. Power should come down, performance should go higher. What about the area? Is my device going to be the older versions, like the bigger device, or is it going to be a smaller device? It could be a handheld device or a thumb device. The area should come down, right. So always when you are talking about VLSI product, the focus at every stage is optimizing this PPA. We want power to be lower, performance to be higher, area to be lower, and all of this VLSI, all the techniques whatever we are trying to do, end of the day the optimization or the requirements would be for a specific PPA functionality only. We want power to be less than, let us say, 70 milliwatts. We want performance to be, maybe the clock frequency should be 1.2 gigahertz and these things. Area of the die should be less than certain, maybe 1.2 millimeter square. That's my requirements here, and based on this requirement the entire process flow comes in. Now if I have to validate this mobile SoC right up front, how can I do it? That is what is this SoC level design and verification flow helps one to achieve it, right. So if you want to test this performance power right when you're designing, when you're speccing out itself, it can really cut down on the entire life cycles of your VLSI product. So the time it takes from the requirements till the actual product is available, if you can do that level of analysis, what the actual product is going to do right up front when you are trying to architect that device, that is going to help you to optimize the overall times. That is what we call as a performance and power architecture analysis SOC. So that will help. The next is, see, for mobile, just the hardware is not sufficient, right? See, you are seeing different versions of the different companies providing different mobiles, right? And we always say, hey, this company mobile is better than the other company. The processor might be the same. They may be using the same Qualcomm processor or MediaTek processor or maybe Intel processor. The processor remains same. But when it comes to the actual application usage, right, the performance of that mobile may be different. And why does it happen? Because of the integrated software. So software, integration of the software along with the hardware actually makes the entire product. So you need to be able to test your hardware along with the software. So if I talk about a system level SOC design and verification flow, I should be knowing how to enable the software as well along with my hardware, right? And then comes the block level verifications. In block level verification, we have seen the formal static verifications, right? The formal verification, you have simulators, right? You have the block level simulators here, which does the block level verification. If you want to do SOC verification, we have emulators, you have prototypings, right? So all those things. In fact, if you look at these three structures, these are the three other verticals as well, which will help you to start a career in the VLSI. Are you going to target your block level engineer, or if you are interested in the software as well, you have career opportunities in the software. See, it's all about identifying your skill set. If you say that, okay, I don't know nothing about any of these things, I want to start my career, start picking up the digital design, most basic. Start picking up the analog device and designing, CMOS concepts, most basic things. Create a strong base. Once you have the strong base, you learn one of the languages which are needed, which the industry is expecting from you. Industry is looking forward, say all these initiations by the governments and the colleges and maybe the different industry persons is to enable the new graduates or undergraduates or postgraduates with these new levels of skill sets. Identify, enroll yourself into those programs where you have access to those softwares which are needed for industry. Prepare yourself on those, learn, give yourself some time. See, the moment you learn something, a new course on VHDL or Verilog or SystemVerilog, you cannot land a job immediately. You should have hands-on experiments. Do lot of codings on those things. Learn those things, apply the codes and learn as much as possible, and learn by failures. See, always it's very important that you know how to resolve an error. It's not about writing a perfect code. There is no perfect code. It's all about how you can fix a specific issue. It could be a compile error, it could be a simulation issue, it could be an issue where you're not able to meet the requirements of your design at all. The A plus B is doing A into B or whatever it is. How can I debug those things? That's what industry is looking for. Do the things where you can learn, where you have hands-on experience, where you can resolve the compile time issues, where you can resolve the runtime issues. Then look at the adjacent things. Sometimes you think that, hey, I am equally interested in VLSI and software also. Learn the C++ algorithms, data structures on that, and prepare yourself and be the one who industry looks forward to meet you, right? So be that person where you can achieve the things. I think we have a phone call. Hello. Hello.
Hello.
Hi.
Good morning, sir.
Morning.
సార్ నా పేరు సాయి లక్ష్మణ్ సార్. నేను ఇక్కడ నిజామాబాద్ నుంచి కాల్ చేస్తాను సార్.
చెప్పండి
సార్, ఇప్పుడు వెరిఫికేషన్ టూల్ తో పాటు అడిషనల్ గా వేరే టూల్స్ కూడా ఏమైనా నేర్చుకోలేదు సార్ మ్యాండేటరీగా?
ఒకసారి మళ్ళీ రిపీట్ చేయండి. ఏ టూల్ అండి?
సార్, డిజైన్ వెరిఫికేషన్ తో పాటు మనం అడిషనల్ గా టూల్స్ ఏమైనా నేర్చుకుంటే మాకు అడ్వాంటేజ్ ఏమైనా ఉంటుంది సార్?
రైట్. ఐ థింక్ మనం ఈ ప్రెజెంటేషన్లో కూడా ఏమన్నా అంటే డిజైన్ అండ్ వెరిఫికేషన్ సైడ్ వెళ్దాం అనుకుంటే మీరు ఫస్ట్ థింగ్ ఈజ్ డిజైనింగ్ ఆర్ మేబీ డిజిటల్ సైడ్ అనలాగ్ సైడ్ డెఫినెట్గా అది నేర్చుకోవాలి. మీరు స్ట్రాంగ్ ఫౌండేషన్స్ ఉండాలి మీకు. CMOS రైట్, ఐ మీన్ ఫిన్ఫెట్స్, న్యూ టెక్నాలజీస్, వాటి మీద స్ట్రాంగ్ ఫౌండేషన్స్ ఉండాలి. ఫ్యాబ్రికేషన్ ఫ్లో మీకు తెలిసి ఉండాలి ఎలా ఉంటుంది. బికాజ్ ఒక VLSI ఇండస్ట్రీలో మనం వెళ్తున్నామంటే మనకి దానికి తగ్గట్టుగా మనం ప్రిపేర్ అయ్యి ఉండాలి. సో డిజిటల్ సర్క్యూట్స్, అనలాగ్ డివైజెస్, CMOS, ఫిన్ఫెట్స్, మ్యానుఫ్యాక్చరింగ్, సో ఈ బేస్ మీరు కవర్ చేయండి ఫస్ట్. ఒకసారి కవర్ చేసిన తర్వాత మీరు ఒక లాంగ్వేజ్ పిక్ చేయండి. మీరు లెట్స్ సే డిజిటల్ సైడ్ వెళ్దాం అనుకుంటున్నారు, సో హార్డ్వేర్ డిస్క్రిప్టివ్ లాంగ్వేజెస్ ఉండి వెరిలాగ్, లైక్ ఒక లాంగ్వేజ్ వెరిలాగ్ ఆర్ VHDL ఎక్కువ పాపులర్ ఉండేది పిక్ చేయండి. లెట్స్ సే వెరిలాగ్ రైట్, ఆర్ మేబీ SystemVerilog. మీరు వెరిఫికేషన్ సైడ్ కూడా మీరు కవర్ చేద్దాం అనుకుంటే SystemVerilog పిక్ చేయండి. SystemVerilog ఈజ్ బేస్డ్ ఆన్ వెరిలాగ్ ఇట్ సెల్ఫ్. సో SystemVerilog కవర్ చేస్తే మీకు HDL కవర్ అవుతుంది, అంటే హార్డ్వేర్ డిస్క్రిప్టివ్ లాంగ్వేజ్ కవర్ అవుతుంది. HVL అంటే హార్డ్వేర్ వెరిఫికేషన్ లాంగ్వేజ్ కవర్ అవుతుంది. ఆ లాంగ్వేజ్ మీద మీరు చాలా ఎక్స్పెరిమెంట్స్ చేయండి, రన్ చేయండి. ఐ థింక్ మోస్ట్ ఆఫ్ ద ఇండస్ట్రీ స్టార్టింగ్ పాయింట్, కెరియర్ మీరు స్టార్టింగ్ పాయింట్ చేద్దాం అనుకుంటే ఈ 2 థింగ్స్ వెరీ ఇంపార్టెంట్, ద డిజిటల్ నాలెడ్జ్ ఆర్ అనలాగ్ నాలెడ్జ్ అండ్ 1 HDL లాంగ్వేజ్ రైట్. మీరు అనలాగ్ సైడ్ వెళ్తూ ఉంటే ప్రాబ్లీ అక్కడ వెరిలాగ్ A అని నేర్చుకోవాల్సి వస్తుంది, వెరిలాగ్ అనలాగ్ రైట్. సో ఆ సైడ్లో మీరు నేర్చుకోవాలి. సో మీరు ఒక స్టార్టింగ్ పాయింట్ మీకు కావాలి అనుకుంటే మీరు డిజిటల్ సర్క్యూట్స్, అనలాగ్ సర్క్యూట్స్, ఎందుకంటే మీకు ఏ ఫీల్డ్లో మీకు జాబ్ ఆపర్చునిటీస్ వస్తే మీకు తెలియదు అనుకుంటే ఇది కవర్ చేయండి. ఇది మీకు కోర్స్ కరిక్యులంలో వెరీ వెల్ స్ట్రక్చర్డ్గా ఉండి, ఐ థింక్ కరెంట్ కోర్స్ 3rd year and 4th yearలో అనలాగ్ అండ్ డిజిటల్ డిజైనింగ్ కాన్సెప్ట్స్ చాలా స్ట్రాంగ్ ఉండి, దాంట్లో మంచి రెఫరెన్స్ బుక్స్ ఉండి అవి వాటిని కవర్ చేసుకుంటూ ఒక లాంగ్వేజ్ పిక్ చేసుకోండి. ఇట్ కుడ్ బి వెరిలాగ్ ఆర్ VHDL అండ్ ఒక మినీ ప్రాజెక్ట్స్ చేయండి. మీరు కోర్స్లో ఉంటే 3rd year నుంచి మీరు లెట్స్ సే 4th yearలో ఉన్నారు, 3rd yearలో ఉన్నారు, మీకు ఎప్పుడు టైం దొరికినా కూడా మేబీ ఒక వీకెండ్స్ కూర్చొని ఒక బ్లాక్ డివైస్ డిజైన్ చేయండి. మీకు టూల్స్ యాక్సెస్ లేదనుకుంటే నేను చెప్పినట్టుగా మీరు ఫ్రీ యాక్సెస్ టూల్స్ ఉంటాయి కొన్ని చోట్ల. ఒకవేళ ఐకోల్ లేదు నాకు అసలు వెరిలాగ్ లాంగ్వేజ్ రాదు అనుకుంటే ఇంటర్మీడియట్స్ ఉండే అక్కడ ఎన్రోల్ అవ్వండి. అక్కడ మీకు డిఫరెంట్ ఇన్స్టిట్యూట్స్ ఉండే వాళ్ళు మీకు ఆన్లైన్ కోచింగ్ ఇస్తున్నారు, లైవ్ కోచింగ్ ఇస్తున్నారు విత్ యాక్సెస్ టు ద టూల్స్. అలాంటి వాటి చోట్ల మీరు యాక్సెస్ చేయండి. ఎందుకంటే ఆపర్చునిటీస్ మీకు రావట్లేదు అనుకుంటే ఈ మెయిన్ రీజన్స్, మీ స్కిల్ సెట్ మ్యాప్ కావచ్చు, మీ లాంగ్వేజ్ అక్కడ మ్యాప్ కావచ్చు. సో మీకు లాంగ్వేజ్లో నేర్చుకోవాలంటే మీరు ఇండస్ట్రీలో మోస్ట్ వైడ్లీ యూజ్ లాంగ్వేజ్ మీద ఫోకస్ చేయండి. వెరిలాగ్, SystemVerilog మీద ఫోకస్ చేయండి. అవి ఒకసారి మీ లాంగ్వేజ్ మీకు వచ్చిన తర్వాత డెఫినెట్గా మీకు ఆపర్చునిటీస్ వస్తాయి. నాకు తెలిసి ప్రతి కంపెనీ దెర్ విల్ బి డౌన్ ట్రెండ్ నౌ, బట్ ఇన్ నెక్స్ట్ ఫ్యూ మంత్స్ ద థింగ్స్ మే చేంజ్ అండ్ ఇట్ విల్ బి ఇమీడియట్లీ అవైలబుల్ టు యూ. సో మీరు ఆ కెరీర్ ఫోకస్ చేయాలనుకుంటే లాంగ్ టర్మ్గానే ఫోకస్ చేసుకోవటం మంచిది. ఓకే, సో I think this is my last slide. So the thing which I want to capture in this specific slide is how can I perform the system level validations. It's important for us to understand just doing a verification at a block level is not sufficient. There are tools and technologies and requirements which will a verification engineer has to use when they are trying to verify at a system level, right? So this system level testing and requirements may not happen. Maybe we should say that it should not happen once the product is available. Rather, we should do it upfront during the design and verification phases. That's the SOC design and verification flow. Just want to give a capture to you. I understand that there could be a lot of things which are new here for you. The idea is not to scare you about, okay, what all this is verification. In fact, you should think about it in this way. There are so many requirements in the verification. Now, if I start building my this thing, verification field is going to give me a long career path where innovations are possible, where your career growth is present, and you can really achieve to very high levels within the industry as well. And this is one of the industries where they take in from the, and I would say that, I mean, there are a lot of VLSI engineers are available, or maybe the electronics engineers are available who are going towards the VLSI field. So it's a field, it's a niche field, but it's a field which will give you a lot of opportunities to get into that also. Keep applying for those companies which are taking a lot of like a bulk of the things. If you are still not able to get into that, if you are still a graduate or doing a BTech, look for the higher opportunity, look for higher courses in masters and from a good college. That can definitely help you to build a strong career and a long career in the VLSI field. I think that's where I would like to end here. Any questions? I think we can take it. Otherwise, this is my last slide. Okay, Thank you. We will be continuing with this different series in next week or probably the following week. Please continue to invest in your VLSI learnings and new features, and good day. And I would like to thank you all for giving me this opportunity to talk about the verification field. Thank you and all the best.